So let us now discuss how to see which resonating or the contributing structure will be making more contribution towards the resonance hybrid. Okay, so let us do it now. So the number one point here is, if the resonating structures are indistinguishable from each other, that is, they cannot be differentiated from each other, then they will be having equal energy and they will make equal contribution. So number one is indistinguishable structures. Okay, so for example, if we take benzene ring, I write one structure, then we write the second structure. Now, in these two structures, the number of double bonds, carbon-carbon double bonds, number of carbon-carbon single bonds, everything is same, right? So it will be like these two structures will be making equal contribution towards the resonance hybrid. Similarly, we can take the example of CH3NO2 again. CH3 and NO2. Now, if you write the resonating structures for this molecule, both are indistinguishable. So there is one nitrogen-oxygen single bond. Oxygen is carrying a negative charge, nitrogen is carrying a positive charge, and one nitrogen-oxygen double bond is there, one CH3 group is there. Everything is same. So these two will be having the same energy. So they will be showing the equal contribution towards the resonance hybrid. Okay. Then the second one is, if a resonating structure is having greater number of covalent bonds, if they're having greater number of covalent bonds. In the last video, I think I just in flow said that sigma bonds will be the same. Sigma bonds will be the same. Number of pi bonds will be different. It can be different. Okay, number of sigma bonds will be the same. Number of pi bonds can be different also. So if greater the number of covalent bonds in the resonating structure, greater will be its contribution. Now we consider this molecule. So you will be able to recognize this molecule. This is the 1,3-butadiene, which is the lifesaver. It explained as the conjugated system. So now we write the resonating structure for it. Okay. So it is CH2. Now, because electrons are moving away from this carbon, this will carry a positive charge. Now it is moving here in between these two carbons. So it will be having a double bond. Then because these electrons are moving on this carbon, so it will be carrying a negative charge. Right? Now we have shown the movement towards this direction, towards the right direction. But if we show the movement towards the left direction, you don't need to write it or show it again. You can just directly write the structure. I'm just explaining it to you. Okay. So now here it will be like this. It can also be like this. So the third resonating structure possible here is CH2. So this will be carrying a negative charge. Then we will be having CH double bond CH and CH2 with a positive charge. Okay. Now, if you count the number of covalent bonds, what is a covalent bond? Bond formed by sharing of electrons. So number of covalent bonds in the structure number 1. So this is just like structure number 1. So this carbon is forming 4 covalent bonds. Sigma and pi bonds, both are the covalent bonds because both are formed by sharing of electrons. So if we consider, we open up this structure and write all the covalent bonds, we will find, so sorry, this hydrogen is not there. C, H and H. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So how many covalent bonds are there in this structure? 11. Right? Now move to this structure. So these two structures will be having the same number of covalent bonds, right? Now in this case, the covalent bonds will be like this. Okay, you can just open it up and write. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So here we have 10 covalent bonds. Here we have 11 covalent bonds. So this structure will be making more contribution towards the resonance hybrid. Clear? So let us move to the third pointer. Let me just clear my screen. Okay. Then the third one is the structures having a negative charge on more electronegative atom are more stable, so they contribute more towards the resonance hybrid. Third point is structures having negative charge on more electronegative atom contribute more. So now suppose we have a structure where we have this carbanion. Do not get confused with what is carbanion. Carbanion is carbon carrying a negative charge. We will be discussing it in detail, okay? So here, this negative charge and this carbon-oxygen double bond, they are in conjugation. So I can move it here. This will move here. Now, so here the oxygen was having 2 electron pairs with it. Now it is having 3 electron pairs with it, and it is carrying a negative charge. Now, because oxygen is more electronegative than carbon, so it will be able to hold the negative charge in a better way. So this one will be more stable. So structure 1, structure 2 will be more stable, and it will contribute more towards the resonance hybrid. Done? Then let us move to the next point. The next point is, if there is a separation of charges, between in the structure, separation of charges in the structure, then it will be less stable. It will be contributing less towards the resonance hybrid. So the fourth point is separation of charges. So these are all very, very important points. So when we will be writing the resonating structures, we will need to take care of these things, okay? Separation of charges. So CH2 double bond CH, single bond CH, double bond CH2. 1,3-butadiene. Now, this is the one possible structure. This is one possible resonating structure. The second possible resonating structure is this one. Positive. And the third one is, we have already drawn it. You can see there. Here it is, positive. Now, we are having separation of charges in this structure number 2 and structure number 3. Structure number 1 does not have any separation of charges. Fine. Now, in this case, what will happen? Negative charge and positive charge, they have a tendency to come together. We know negative and positives, they attract each other, right? Now, to keep them separated, we need to supply energy. They will be consuming energy. They will be absorbing energy to keep these two structures, these two charges separated. This means the system's energy will increase and its stability will decrease. So it will contribute lesser towards the resonance hybrid. Simple. Okay, so if there is a charge separation, the structure will be less stable. If there is no charge separation, the structure will be more stable. Suppose there is only negative charge in a structure, it will be more stable. If there is only positive charge in a structure, it will be more stable. Okay, then the fifth point is, if similar charges are present on two atoms which are adjacent to each other, if similar charges are present on two atoms which are adjacent to each other, then the structure will be unstable. It will be contributing lesser towards the resonance hybrid. So we can consider the example of diketone. So this is a diketone. Now I can write it like this, just like, because this oxygen is having more electronegativity than carbon, so it can attract the pi electrons towards itself, right? Now the second structure possible will be if both the pi bonds, they shift to the oxygen atoms, what will happen? Oxygen will carry a negative charge, carbon will carry a positive charge. Here also oxygen will carry a negative charge, carbon will carry a positive charge, and this one. Now what is the tendency of the similar charges? They repel each other. If the two things are repelling each other, will they be able to stay together? No, this means there will be instability. So it will lead to an unstable situation. So this second structure will contribute less towards the resonance hybrid. Structure number one is more stable. Good enough? Okay, then let's move to the next point. Now the next point is about positive charge. If a structure is having delocalization of positive charge on more than one atom, if a structure is having delocalization of positive charge on more than one atom, it will be stable. So we can just consider, we can take the example of this carbocation. Now see, here you will be learning one more new thing. Firstly, we did it simple, that how to recognize a conjugated system. We did 5 pointers where we could recognize a conjugated system. Now we are moving a bit towards complexity. In this structure, if you see this positive charge and the lone pair of electrons on oxygen, they are sitting at one bond distance. They will also be in conjugation. Okay, this means these electrons, they can move towards their side, and oxygen will carry a positive charge. Now here in this case, the second structure, it is making the positive charge of this carbon more stable by delocalizing it. Okay, carbon was having a burden of positive charge on it. Now this oxygen atom, what it is doing, it is decreasing that burden on it. So they are sharing their electrons. Oxygen is giving its lone pair so that carbon can be comforted. Okay, you can take it like that. So if you have some kind of burden and somebody comes in and just share that burden with you, what you will feel relaxed, you will be stable. Similarly, if positive charge is delocalized by some atom which is carrying a lone pair of electrons, it disperses the negative charge, and if it disperses the positive charge, and the structure becomes stable. Okay, so this is for positive charge. For the negative charge, we have already discussed that it should be on more electronegative atom, right? Then the seventh point is the structure which is having complete octet of all the atoms except for hydrogen, because it is going to have only a duplet of electrons, only 2 electrons will be there with hydrogen, and all the other atoms involved in that structure, if they have octet, complete octet, that structure will be considered more stable. For example, if we take this, okay, if this structure is there, now this positive charge and these lone pairs, again there is one double bond between the two. There's one double bond between the two. It is not necessary that it should be only a single bond. There should be one bond distance. The bond can be single, double, triple. Triple is not the case. Okay, it will be it is at a higher level. You don't need to go into it. Okay, now what will happen? This can move here and it will be dispersing the positive charge of carbon. Now, what will be the resultant structure? The second structure will be oxygen will carry a positive charge. Now, see the octet. In this structure, this carbon is having only 6 electrons. There is 6 sets of electrons. This is 1 pair, 2 electrons. 2 electrons from this bond, 2 electrons from this bond. I think you can see it, right? So total of 6 electrons are there. But in this case, this carbon is having these 6 electrons and 1 pair from this. So this carbon is here, it is having 8 electrons. Here it is having 6 electrons. Now come to oxygen. How many electrons are there in oxygen in structure number 1? On oxygen in structure number 1. 1, 2, 3, 4, 5, 6, 7, and 8. It is having 8 electrons. So 1, 2, 3 from 4 from these this double bond, then 2 lone pairs are there. So 8 electrons with oxygen. Here also oxygen is having 8 electrons because this lone pair is also there. Still it is having 1 lone pair. 1 it is sharing, 1 it is having. So 6 electrons from these this triple bond and 1 from lone pair. So again, it is having 8 electrons. So in this structure, all the atoms except for hydrogen, which is going to have 2 electrons, all other atoms, they have complete octet. So this will be more stable. So these are the 5 criterion to know whether a structure will contribute more or less towards the resonance hybrid. Good enough? So this is quite simple. Now in the comments below, you need to write the 7 points that you have understood about the contribution of the resonating structures towards resonance hybrid. And I will be discussing the resonance plus R and minus R effect in case of benzene ring that you find horrible, and I will be making it simple. So in the next video, I'm going to discuss that.